Rudolf Rossa to present his work on cross-lingual transfer of dependency parsers. So the turn is yours.
So, yeah, welcome. So I will try to present my, well, actually several years of my research now on the cross-lingual transfer of dependency parsers. So first, what is this parsing actually? So what I understand by parsing in this talk is that the problem is that I have a text in one language, a target language, say it can be Slovak or any other language, like Rudolf ľubí vlaky, which means Rudolf likes trains. And what I want to get is the syntactic tree representing the structure of that sentence. So, like for example, this one, which is universal dependencies tree. So we want to know that the verb ľubí is the root of the sentence. Sorry. And that Rudolf is the subject, the nominal subject of the sentence, and depends on the verb. And the same with vlaky, which depends on the verb, but this is the direct object in the sentence. So so this is what we want. Okay. Now, how do we get that? So in case we do have a tree bank in the target language, so we have a Slovak tree bank, then the problem is quite easy. We take a parser and train it on the data. So in my experience, I often use the UD pipe, which is nice because it also has a tagger inside. And then we just apply the parser onto the text, and we get an analysis. So this is like the easy task, which I'm not so much interested in. It gets much more interesting when we don't have the target tree bank. So imagine that we have maybe a tree bank for Czech language, but we don't have for Slovak language, which was the situation like 5 years ago still. So what can we do? So I will just now show a very brief idea of what you can do, and then the rest of the talk will be going into details on how exactly can we do that. So the main idea is to take the tree bank for another language, I'll call it the source language, so for example Czech, and translate it into the target language using some machine translation system like Moses or anything else. And by that we already converted it to the previous case, so now we do have a tree bank for the target language. It's not a manually annotated tree bank, it's a pseudo tree bank automatically created, but still we now can use the previous approach, train a parser on the tree bank and parse the text using the parser. So that's the main idea of everything I'm doing. Of course, it's fair to say that there is another option that I'm not doing in my work, and that's like if you want to parse Slovak, let's just annotate some Slovak data and then you can train the parser on that. And that's of course like a recommended way to do things, because you will probably get better results when you really have data for the language or for the task that you want to solve. A slight problem might be that there's just too many languages, and it's we cannot probably expect anywhere in the near future to have annotated data for all of the languages in the world. So the current situation is that we have tree banks manually annotated for about 70 languages, but there's like about 100 times more languages for which we don't have anything, so we just have to use some of these methods. And even for the languages for which we do have the data, then it's usually annotated on news texts, on books, on Wikipedia, on kind of nice sentences. And what people have found is that then the tools that you train on such data don't really work well on other kinds of data, like data from the web, from the Twitter, Facebook, all of these. It's kind of half new language actually. So there is kind of a link between these cross-lingual methods and between domain adaptation even within the language. So It's changing a bit. Now a lot of the tree banks include such weird data. But for many years, people were just saying, yeah, we're doing Wall Street Journal science because we knew very well how to work with Wall Street Journal, but we didn't know how to work with other texts, really. Now, how well can we get? So this is these results are actually very good. What I'm showing here, usually you don't get such good results. So here, the cross-lingual system is the red one, which we submitted into a shared task in January, and actually we managed to win the shared task with the system. So you can see that it has accuracies between like 60 and 80%, so that's good for a cross-lingual methods. Usually you get around like 50% or less. And you can still see that usually we don't reach the supervised parser. So the yellow one, this is when you use the target language data. So for example, for this Slovenian and Croatian, if we have a Croatian tree bank and just train a parser on the Croatian tree bank, we get around 70% accuracy. When we don't have that and transfer the information from Slovenian, we get about 10% less. Which is kind of a big drop already. And I'm saying this is like very strong results. We invested a lot of time into that to tune the system for each of these three setups. And so you couldn't do that really for thousands of languages. So you would have lower results. An interesting thing happened for Czech and Slovak actually, where the cross-lingual setup managed to get better than the supervised one. So this is when we use the Slovak tree bank and train on it, and this is when we don't use the Slovak tree bank, just use the Czech tree bank and translate it into Slovak and train on it. I think it's a combination of several things why this happened. One thing is that the supervised parser was actually a bit weak. Like 70% is a low number. It should be about 80 or more. But it was trained by the organizers of the shared task, so we don't know. And also with Czech, the situation is quite specific because the Czech tree bank is enormous. For most languages, you don't have that. You have like 1% or 10% the size of the Czech tree bank. And the Czech and Slovak are very close. So this is like the ideal situation that can happen to you in cross-lingual parsing. So you have two languages which are very similar. And for the source language, you have lots and lots of data. So it's very easy to do the cross-lingual transfer. So in most cases, this won't happen, and you will have something like the 60% or even less. But we would like to get, of course, to the level of the supervised parsers. Okay, so that was the introduction, just that you know what comes in the talk. Now we'll look at it in more detail. I'll still add a bit of motivation, like why do we actually do that parsing, and how do we do it even in the monolingual case. And then I'll look at kind of the beginnings of the cross-lingual parsing, where we didn't use machine translation, we did Delexicalized parsing. But it turned out it's better to add the machine translation, but it's not simple, so I'll look into why it's not simple, how we can solve all the problems. There will be a lot of unsuccessful experiments of mine here. And then towards the end of the talk, I will look at kind of some extensions to the setup. So previously I just said, yeah, let's use maybe Czech if we want to parse Slovak. That's nice, but if you want to parse, I don't know, Tamil, so how do you know which source language to use, whether it's better to use English or Czech or Hindi? Well, you might guess, but we might want to have something more principled. And as I said, we have resources for about 70 languages, so maybe we could even use multiple resources and combine them together. So all of this is coming towards the end. Fine. Why to parse the text? So the simple answer is, well, to understand the structure of the text, which is kind of a path leading to understanding the meaning of the text, potentially. why do we really do it? What do we use it for? So I would say in formal linguistics, I'm not a formal linguist, so my take is that what automatic parsing is useful for is for analyzing the corpora for doing corpus linguistics. So if you want to study verb valency, so you need to know what's the main predicate in the sentence, which arguments it has, and automatic parsing can, well, it's not 100%, but it can give you a good estimate like what the arguments of the verb are. So it can help you to study more interesting phenomena in the language. In computational linguistics, well, traditionally parsing was used as a pre-processing of the text for other tasks. So if you wanted to do, I don't know, machine translation, so the idea was that you first parse the text, which then helps you to do the machine translation better, with named entity recognition, whatever you want to do. Currently, this is kind of shifting away from that approach, or it has probably already shifted, I could say. So now, what you usually do when you want to do, I don't know, named entity recognition, so you don't bother yourself with parsing the text. You just label some text data with named entities, and then you use a neural network, which is an end-to-end system. So in goes just plain text, and out goes already the labels you want. So you don't need these several steps of processing by, well, you often use tokenization, but maybe you don't even have to use that, and you don't need tagging and parsing and whatever all steps. You can just train one system. But it's good if you do have these label data for the task you want to do. So for like machine translation, that's easy. You just take parallel text, you can train on it. For many tasks, you actually don't have any data. You just have little data that you cannot train the network on. So then that's where I see the main use of parsing and other of these processings today, where anything can really help you solve the task. Like you want to do maybe coreference resolution, and if you don't have data annotated with reference, you might still invent some rules, some heuristics to solve the task, and then any abstraction over the input is useful to have. So nowadays I see most of use of parsing in like smaller tasks with not enough data. So a bit of how do the parsers work. So if we want to do the parsing cross-lingually, so it would be good to know how it works monolingually, at least in one language. Yeah, I'm doing just dependency parsing. It's important to say. So now it seems to be the more popular branch of parsing, with the phrase structure parsing just being, well, not forgotten, but less popular nowadays. So in dependency parsing, the task can be formulated as a machine learning task, where for each word in the sentence, you need to determine what's its head word and what's its relation to the head word. So for example, for Rudolf, we want to say that, okay, this depends on likes and not on trains. And what's its role in the sentence? Well, it's a nominal subject. So this is what we want to determine. And so to do that, so for as with any machine learning, you need some kind of representation of the input with features, and that's basically what's the most important parts of information for the parser. So what helps it say like where the edges are. So well, actually the strongest feature already is something very independent of language. And that's just word distance. So if you have a sentence, so most of the words that belong together are just next to each other. So most of the edges have a length of 1, 2. Then there is the word order, which goes together with the word distance, of course. But there is the other thing of the languages having a tendency to left or right branching, like most of the edges lead to the left or most of the edges lead to the right. That's not true for all languages, but there seems to be a tendency in many of them. Now, what's really the killer feature, the feature that brings the highest improvement in accuracy when you include it, is the part-of-speech tags. So when you represent the sentence just with the part-of-speech tags, even using like a set of 10 or 20 part-of-speech tags, you already can have a very good guess on what the structure of the sentence will be and what the roles of the words in the sentence will be, even without looking what the words actually are. And it turns out that it's still useful to look at the words, of course, but it's mostly for disambiguation. And I'll show that in the next slide. And so once you have this machine learning, so it kind of predicts how good each edge would be, and then you still need kind of inference algorithm to come out with the parse tree in the end. So even if you, for each word, if you say what's the head word and what's the label, so maybe the output is not a tree, so you still need some kind of processing to ensure that what comes out is really a dependency tree with one root and no cycles and so on. The two most popular algorithms are graph-based algorithms like the Mst Parser by Rand McDonald and the transition-based parsers by Joachim Nevre and other people. And I'll show a bit how the Mst Parser works. Why we need lexicalization. So I want to show two things. So first, if I just have the part-of-speech tag, so I know there is a pronoun and a verb, so I can already guess that probably the pronoun will be the subject of the sentence and will depend on the verb, even without looking at the words. Or I have a burger, so there's a determiner and a noun, so that's quite easy to guess that there will be an edge between the determiner and a noun. But actually, these two sentences have the same sequence of tags. They don't have the same structure, because there is a big difference whether here the noun fries is part of the meal that you're eating. So it's a modifier of the burger. What kind of burger? Burger with fries. Here it's something different. The noun is hands, and that's not part of the meal. That's the way how you eat the meal. How do you eat it with hands? So that's an oblique relation in the new UD. So that's like an adverbial. So for this, you really need to know the lexical information from the words. But otherwise, you can guess the structure quite easily, even without having the lexical information, just from the part-of-speech tags. So that's an interesting observation. Now, just briefly, because I will be using it later in the talk. One of the parsers, maximum spanning tree parser from 2005. So how does it work? It's called graph-based parsing. That's because it starts by creating a graph. So if the sentence is Rudolph likes trains, then I create a node for each of the words and a virtual root node. Then I add all possible dependency edges. So it's a near complete graph. And now the magic happens. So I have to get a score for each of the edges. And this is what comes from the machine learning now. So there is a trained model from data, and it predicts how good the edge is. So like this edge from Rudolph to trains, well, it's from a noun to a noun, so that's good. It could be a noun modifier or a compound noun or something. So the score of the edge is positive. But there is also the problem that there is a verb between the two nouns, so that's a bad feature, so this will lower the score a bit. So that's trained from the data, and you get a weighted graph in the end. And then it's called the MST algorithm, or maximum spanning tree algorithm, because then you find the maximum spanning tree, so-called. So that's like the edges with the highest weights. So we get a structure of the tree. Now that's unlabeled. It doesn't have the relations yet. In the classical MST parser, you just use a Markov chain label like with tagging to label the edges. But there can be other approaches. You can do the labeling jointly with the parsing. And with the transition-based parser, it looks a bit differently. But there's like one way you can do parsing. And a successful way. Still used today. Okay, so that was the introduction to parsing in the monolingual setting. So now let's bring it to the cross-lingual setting. Let's train a parser on one language and apply it to another language. And this has first been done with Delexicalized Parsing. So the delexicalization, it means you remove the lexical information from the data. So if your tree bank has the sentence Rudolph likes trains, and you know it's a noun and verb and noun, so what you do is you delexicalize it, so you just keep the part of speech tags, and you hope that it will be enough to parse it. And as I said, well, it's already pretty strong. You're missing some disambiguation, but in most of the cases, this is sufficient to get the correct structure. And basically, roughly, if you have a supervised monolingual parser, you can get maybe around the 80s in accuracy with the lexicalized one. And if you remove the words, you get about 5%, 10% lower. So still not bad. So that's one reason why this might be a good idea. And the other one is that thanks to some research and thanks to some annotation efforts, we now have actually several sets of so-called universal part-of-speech tags. And the idea is that they are more or less shared across all the languages, so that in most languages you can say, well, this is a noun, this is a verb, this is an adjective, something like that. It's not perfect, but it's pretty good. And once we have that, so when we avoid the lexical features, we don't need to bother ourselves with some machine translation, because that's complicated. And even we have a universal parser, when the parser just looks at part of speech tags, so it doesn't have to care about which language it is, as long as it has the same part of speech tags. So you can even easily combine multiple languages, because if all of them use the same tags, you just combine it simply. And it's still popular today, even though it's better with machine translation, because it's a very simple task. It's easy to experiment with it. So you just remove the words from the tree bank, you train the parser, and you're done. You just apply it to another language, and that's fine. So basically, all of the first experiments with cross-lingual parsing were done on the Delexicalized one. Of course, it's really crucial that the languages really use the same annotation, so the same part of speech tags. So this has been identified from the beginnings of the task, of course. So this interset that's actually invented by Danzemann, based on his first experiments with Delexicalized parsing, because he needed to come up with some interlingual representation of morphology of tags and morphological labels. And then the effort started at UFA, where I guess in the end it was 30 tree banks of different languages were collected, and all of them were converted into the same annotation style. So interset for morphology, and then something based on Prague dependency tree bank for syntax. It was adapted a bit. For the morphology, the interset was ideologically it's similar to the Prague text set or to Czech text set, but it's like the Czech text set is very much suited for Czech, so there had to be invented something different. Now this turned out to be a good idea, so other people caught up. In Google, they annotated some new tree banks using the same annotation style for all of them. They started, I guess, with 5 tree banks. Then in the next round, they had 12 tree banks, I think. And they used Stanford dependencies for that, which is, well, another popular dependency grammar. Then this turned to be even a better idea. So then all of the efforts joined together under the Universal Dependencies project and under the lead of Joachim Nivre, which now has these about 70 tree banks or what. And it contains existing tree banks converted to this style, but it contains a lot of newly manually annotated tree banks. And now we have this, I think today there is 17 labels for the part of speech tags, which is based on the Google guys' work. There are the universal morphological features, which is based on the work by Danzemann. And there are the universal dependencies relations, which is based on the Stanford dependencies and the Stanford guys. Yeah, when we did our experiments, we found that still, although it should be, the annotation should be the same in all of the languages, in practice that's not always true. There are still some problems. Well, some of them are just because the languages are a bit different, so you can never have really exactly the same annotation for all of them. But some of it is still like the tree banks come from different sources, and yeah, some of the annotators probably misunderstood some of the guidelines, so there are some consistent problems. But yeah, it's very good. So now it's easy to use these tree banks to do Delexicalized parsing, but still it's worth looking at some of the problems and still doing some manual tweaks here and there. So how well does it work actually? Well, it's not perfect. It's maybe useful for something. So this is some older experiments on the Hamladiti tree bank, so the third tree banks in Hamladiti. And the average supervised score is about 80%, and that's unlabeled, so that's just the structure without the dependency relation labels. So if we still use the monolingual supervised parsers and we just remove the words, so we get about 6.5% lower, that's fine. But when we move cross-lingually to another language, we have a drop of about 20 percentage points, which is massive. So basically, yeah, when the scores are about 50, so it really means that half of the edges are incorrect. So that's hardly useful for anything, probably. Well, when you don't have anything else, so that's about the best you can do. But that's kind of weak, and we haven't been able to get much better. I have to warn you. Still, the cross-lingual methods are the cross-lingual parsing has very low scores, so it's still about the 50s, 60s. And not only when you're very, very lucky, you can get to some 70s, maybe. But yeah, like that's why it's research. We want to make it better. Wouldn't be interesting if we already were somewhere here. So that's it. So that's just the drop you get by moving to a different language. So it's the same parser, just trained on part of speech text, but here it's applied to the same language as it was trained on. In here, it's just applied to a different language, and that's all there is. Okay. So as I said, Delexicalized parsing is kind of the older approach. It has two big problems. One of them is like a principled problem, that it assumes that for both the source language and the target language, you have part of speech text, so you have a tagger. But where do you get the tagger? So if you want to parse one of these 7,000 languages, so your chances are that probably there is no tagger. There is just no annotated data. So this assumption is kind of unrealistic. And on the other, even in the other direction, if there is a tagger for a language, so there is a high chance there is probably also a tree bank, so you can just train the parser normally and you don't have to use these cross-lingual methods. But there are languages which do have a tagger and do not have a tree bank, but that's kind of a small group. So really the focus of these methods is very small, narrow. If you don't have the tagger, you can still do cross-lingual tagging. Like when we do cross-lingual parsing, why not do cross-lingual tagging? But for that, you need some parallel text, some machine translation, something like that. So once you already have that, you have parallel text for the languages, so you can also just do lexicalized parsing in the cross-lingual parsing as well. So it's not really clear if the data you have is small, how that works. So the Copenhagen guys investigated it like with really languages for which they only had the text of the Bible and no other resources, and they tried to see how it works. And they argued that in that case, the Delexicalized parsing is fine, but still, like, these are very low scores, so it's hard to say anything about it. So that's like a principal problem. Like, we don't have the tagger, so where do we get the tags? What happened? Yep. Then, of course, when you remove the words, so you just have the tag. So you kind of assume silently that the grammar is basically the same in both of the languages. That if there is a noun, a verb, and a noun, so it means, yeah, that's a subject, predicate, an object, maybe. But that's not true, of course. Languages are different. That's, of course, a general problem for all the cross-lingual methods. Like, if the source and the target language are different, then you will get bad results. But it's even stronger with the delexicalized ones, because the lexical information, as I said, can help you disambiguate some of the cases. Like, I have an example in English and in Italian saying the same thing. Red strawberry and a yellow banana in English, which is an adjective noun language, so the adjectives precede nouns. Whereas in Italian, the adjectives usually follow the nouns. So when you strip away the forms and your parser is trained on English, so it just says, yeah, if there is an adjective, just go to the right until you find a noun, and this will be the head noun for the adjective. Because in English, you don't put the adjective after the noun, so the parser has never seen that and will never try to annotate that. So if you do that in Italian, so probably this adjective will be attached to this banana here, so the tree will be very messy. If you do have the lexical information, so then you have at least some bit of information suggesting, yeah, when the adjective is red and the noun is strawberry, so probably these two go together, right? So even in Italian, if you know that, well, so the direction of the edge is unexpected for the parser, but lexically this makes much more sense than a red banana. So you have a chance of getting it right by introducing the lexical information. This all means that for the delexicalized one, you have to be more careful about the choice of the source language, but you should be careful anyway, so I'll get to that at the end of the talk. Anyway, now the current approaches that we really use. So it's all based on machine translation now. It seems to be the best approach to transfer the lexical information. There are other options. You can just use parallel text and try to automatically parse one half of the parallel text and transfer that to the other half. It was done. It was kind of successful, but machine translation seems to work better. In principle, there are two options of what you can do with machine translation. So we have this target and source. So let's say we have tree bank for Czech. We want to parse Slovak. So either we can take the Slovak sentence and translate it into Czech. So then we can use the Czech parser to parse the Slovak sentence because it's translated into Czech. Then the other option is that we take the Czech tree bank, we translate it to Slovak, and then we train a parser on the Slovak tree bank. So it's kind of symmetric. But it turns out that this other approach works better. So first, well, empirically it gets better results, so why not use it? There might be multiple reasons. I haven't seen an analysis of which of the reasons is the strongest or what, but there's more of them. So one thing is that when you translate first the tree bank from Czech to Slovak, so the output will be a bit noisy because it's output of machine translation. So probably the parser trained on it will be more robust. It will be used to seeing unexpected things in the data, so it won't be so misled by some things in the language. With machine translation in this direction, you can add the text in the target language. So maybe in Slovak you don't have a tree bank, but you have some text downloaded from the web or from Wikipedia, from some books. So for the machine translation, you can use that to train a target language model. So that's a strong component of the machine translation systems, and it will get better results for you. So somehow the machine translation will be more adapted to the target language. And even for the parser, it's actually useful to have some text in the target language, at least for the current parsers, which often are neural network based, as UDPI based. So it's actually, the word forms are represented by word embeddings in it. And if you have large plain texts, you can pre-train the word embeddings on that. So the parser already, when you train it, it has some kind of hidden knowledge about the target language. It doesn't know about the annotation of the language, but at least the word embedding captures something about the language. So hopefully these are the ideas why this works well. And then, of course, there are some technical reasons why this is also nice. So if you translate everything into the target language, so it's much easier to combine multiple languages. So if you have data in Czech, Polish, Slovenian, so you can translate all of that into Slovak and just combine it, mix it, train something on it. In the other way, it's hard. So if you have a Slovak sentence, so you translate it to Polish, to Czech, to what I said, Slovenian, then you parse all of these, and now what? So it's not so simple. And just a small benefit is that out of this approach, the output is one parser that can just parse the target language. So you don't, when you run the parser, you don't need anything special. You just run it in a standard way. Now, as I said, there are a lot of problems with the translation of the dependency trees. And it basically all goes down to the problem of the language is not mapping one-to-one. So if just each word in one language mapped to just one other word in the other language, then everything will be nice. We could just copy the tree structure and keep everything unchanged, and it will be great. It doesn't work that way. Let's say if I don't know, if I have an English tree bank and I want to translate it into Czech, and there is this by, so what do I do with it? I don't know. Or the other way around, I have the Czech sentence, I translate it into English, and suddenly there is a new word, and I don't know anything about the word, like where should I put it, what label should I assign to it? So that's the hardest problem with machine translation of dependency trees, because it's not one-to-one. There's two main approaches that are used. One of them is the one that I use mostly. It's just to ignore that thing and just assume that it's more or less one-to-one, and if it's not, then we don't care. It kind of works when the languages are close enough. So when it's like, I don't know, Czech and Slovak, so yeah, it's mostly one-to-one. There are some things that are consistently not one-to-one. So in this case, it will just make problems, but in most cases, it works fine. And then it's super easy to do, because we just say, okay, we tell Moses to translate it word by word, and we just copy the structure, and we're done. Then what basically all other people do is another thing, to use standard Moses, which is basically M2N, which is phrase-based. So it can translate like 2 words to 3 words, and you don't know which words really map to which words, and it's not really one-to-one, so you cannot really copy the structure. Then there is a bunch of heuristics, which are very complex. You basically have to delete some of the nodes, you have to guess some of the edges, some of the labels, and this adds, of course, a lot of noise. So in the end, the machine translation is better, but the projection of the structure is worse. And it turns out that in the end, the performance of these two methods is very, very similar. It's a bit surprising. So, well, of course, if the languages are distant, so they don't really map one-to-one, so this method already gets better, because the one-to-one method already, cannot capture most of the things in the data. But if you don't have similar languages to transfer between, then the results will be bad anyway, so maybe that doesn't matter so much. And if the languages are similar enough, then you can use this method or that method, and you will get very similar results. this is based on both the results of the shared tasks, where different people use different approaches and the results were similar, and also on, I believe it is this paper by Jörg Tiedemann who actually compared these two approaches and found that the results are very similar. So because everybody does the second thing, so I decided to do the first thing and just try to find how I can improve this one. So I tried a lot of different setups of the machine translation. So in machine translation, you usually do some word alignment. The let's say default tool for that is to use Giza++, and then a decoding system, so the real translation with Moses usually. And I wanted it one-to-one, so you can switch Moses to do just word-based translation. And now, like today, Moses is not the state of the art anymore. Of course, people use neural translation, but still Moses is very good. It's fast to train compared to neural systems and so on. So it's pretty good. I tried other systems. Like Martin Popel re-implemented a greedy monolingual aligner, which assumes that, and David Mareček did a similar implementation, which assumes that words that correspond to each other look similarly. So they use Jarrow-Winkler distance for that, something like Levenstein distance, but pays more attention to the beginnings of the words. And looks at part of speech, which Giza does not. So you say, okay, a noun should probably be aligned to a noun. Again, you need to have the target part of speech for that, and other things. I even tried like my own system, which I implemented, which just doesn't use any parallel data and tries to just guess which word is translated by which word, just based on similarity of the words and frequency of the words. And I tried to combine some of these systems together. But anyway, the default setup turned out to be best. So to use the standard Moses, standard Giza, just switch it to translate word by word. So I can even show that in numbers. So the red ones are the parsing scores. And the third one, you can see that the Giza and Moses setup is like much higher than all other systems. And even in the blue score, so the quality of the translation, it's higher. So yeah, I basically tried a lot of experiments and didn't find anything interesting really. I also tried to play with splitting the words into smaller parts. So the idea is, okay, so if I have go by train, and in Czech that's jet vlakem, so this in Czech is one word. So maybe I could somehow split it into two words. So it could be either really the morphology, like language motivated morphology, or it can be just some subwords based on some information theory algorithms or whatever. And so the idea is when we split it, so maybe it will correspond one-to-one better, and it will also help us with how it's called when we don't have enough data. The data density. So if you split rare words into smaller parts, so they are more frequent, so you will have less problems with unknown words and so on. So it seems like a good idea, but we haven't been really able to get it working properly, because there are too many problems. Like first, so how to split it really? Do you use a morphological splitter or do you use something else? And how do you split? You need to split both of the languages, and you need to ensure that they somehow align to each other. So probably you want to do it somehow jointly. It has been done. There's a typo, Snyder. But it's complicated to do. It takes ages to run, and the results are not very promising. And then when you split it, so how do you parse it? What's the tree structure of this set of subwords? Like, okay, so probably the root should be the root. the morphological root should be the dependency root of the subtree. And then the affixes should be like leaves on that, but it's not that clear. And what label do you assign to this edge? So what does this mean? It's like a suffix, but is it a meaningful label in the dependency tree? And we cannot ever do it perfectly, so it will just add some more noise into it. It's just one more step in the pipeline that will just make some problems. So we basically found out that even if we try hard, we don't still get the one-to-one alignment that we would want in the first case, because in the parallel data, it's not real parallel. If you ever saw some parallel data like Chang or something, so there are missing words, extra words, it doesn't really align well. So even if you split it, it won't help you. It will get you half the way probably. So not all phenomena are solved by that. Like some information just is present in one language and is not present in the other. Like one language has cases, the other one doesn't. So what do you align it to if there is nothing else, no preposition? It's just missing information. So maybe some empty alignments, but then you're getting back to the original problem. Yeah. So they didn't work very well. There is a lot of research on bilingual or multilingual word embeddings. So if the parser already uses word embeddings on the input, so maybe we could use some bilingual word embeddings. So to train the embeddings to map the corresponding Czech words and English words to the same vectors. And like this would solve the machine translation problem even without like doing proper machine translation. So again, I tried some experiments and other people tried some experiments. So this is a nice overview paper which compares about 4 different approaches. And they didn't find any big improvements by any of them. And I tried some more approaches and I also didn't find any big improvements. Usually the results just got worse. It seems the problem, part of the problem is that in the word embeddings, the idea is that the space of the word meanings is kind of continuous. So you can move in the space and the position in the vector space tells you what kind of meaning the word has. But it seems the parsers don't work by that. The parsers seem to just remember some important words. Like they remember, okay, this verb goes with this object. So they are really care about the identity of the words, not their position in the continuous space. So if we do something like interpolating embeddings or averaging them, summing them, so we just end up in a place in the space which doesn't map to anything in the other language, and it's basically unknown to the parser, it doesn't know what to do with it. So what we ended up doing, what worked somehow, is that we just map the words in the 2 languages together, and we use the same embedding vector for both of the words. But then we are probably already losing the advantage of using the word embeddings. And we could just do machine translation if you're mapping words one-to-one. So we didn't need the word embeddings for that in the first place. And machine translation can disambiguate. It can translate one word in different ways, which the word embeddings don't do by default. They just have one embedding for all the words. So didn't work well. Okay. So in machine translation, I'm just stuck with the basic Moses and Giza because it turned out to work best. Where I do have some good results is the multilingual setting in the choosing the source language and into combining the multiple sources. So and this is a very important topic, and we can get great improvements there. Of course, the first experiments often were, okay, we have a lot of resources for English, so let's use English as the main resource, as the source language, and just project every information from English into the other languages. Well, it's maybe easy to do, but it's not very wise because you get very, very low results. So with the proper source language, you get into the 60s maybe. If you always use English, the average will be around 30% accuracy. So that's terrible. That's just completely useless. With the 60%, you get at least, well, some of the relations are okay, so you get at least some information there. Okay, so let's say we have a target language. No. Swahili, whatever. And we want to find, of course, okay, we have these 70 possible source languages, so which one do we use? Well, that's easy to say. So we need a language that is very similar. So it should be the same language family. It should have similar word order. It should have similar auxiliaries. So like some languages have determiners, some of them don't. So if your target language has determiners, your source language should also have determiners. And this is interesting because it's kind of multidimensional. So the languages can be similar in various ways. And so there is nice research into that. Then the other thing that we already saw is that when the source tree bank is huge, it helps a lot. Just there is no data like more data. So it's also reasonable to look at the sizes of the source tree banks, because if you have a perfect similar language, but the tree bank only has 100 sentences, then probably it's not going to help much. But actually, this doesn't sound very interesting. It's probably some linear, quadratic, or exponential dependence. So there is not much actual research into what size of the tree bank works best. Now, so I'll look at the source and target language similarity mostly. So what people have done, of course, is to use the World Atlas of Languages. I don't know what the S is now. Structures, I don't know. Where for many languages you can learn the language family, the word ordering features, the morphological features. There's about 70 different features of the language that you can learn. And you can just use languages that share a lot of these features. It works nice. What I did, what I'll show in the next slide, is you can look at the part-of-speech tags in the two languages and look at the sequences of the part-of-speech tags and look if they are similar, and then probably the languages are similar. Again, the problem is you need target tagging for that, but if you have the machine translation, you can get it somehow. Then what I saw this year is you can use the language identification algorithms, which basically look at character engrams. And the idea is that similar languages have similar character engrams in them. So let's try to look at our target language, and let's try to identify, okay, which of the source languages is it according to the language ID algorithm. It turns out to also work nice. And actually, Željko combined all of these three approaches in his work and found out that if he combines all three of them, then it works even better. And I was happy to see that the approach I invented did the largest contribution in the combination, but all of them contributed a lot. And you can do other things, like Anders Degaard had trained a target language model on part-of-speech tags, and use that to weight the sentences in the source tree bank. It's nice, but you need to modify the training algorithm for that if you want to have each sentence with a different weight. The default training doesn't do that, but it worked nice as well. So I'll just briefly show what I do. So basically just look down here. So let's say the target language is German, and we want to see whether the best source language would be Czech or English or Italian. And we look at the distributions of the tag 3 grams. So a sequence of determiner, adjective, and noun. We can see it often appears in German and in English, but not in Czech because we don't have determiners. Determiner, noun, adjective. So we can see in Italian this inverse order of noun, adjective is frequent. And just start of the sentence and an adjective and noun with no determiner, that's very frequent in Czech. So already by these statistics, even visually, you can see that the graph is the most similar between English and German. So probably the English language will be best source for the German language. Just the bars look similarly. And formally, this can be computed by the Kullback-Leibler divergence, which is actually used to compare probabilistic distributions or distributions. So it really just does basically this. It looks at these distributions and say which are the most similar. And this turned out to be quite successful. So in about 50% cases on the data set I had with 33 banks, so it was able to identify the best possible source tree bank for the target language. So that's good. If there was no really similar tree bank, then it didn't work so well. But anyway, that's already fine. as I said, the problem is that I need a target tagger for that, but it seems even with the cross-lingual part of speech taggers, it is promising. It can be used. So that's kind of a technical but good way of identifying similar languages. Now, moving to the last topic. When we know how similar the source and target language is, we can use it basically for two things. So one thing is, okay, I have these 30 tree banks. Which one should I use as the source tree bank? So to select the best source. So that's what I showed with this 50% accuracy I had. The other possibility is, well, if we have so many tree banks, so we could probably use more of them and just give different weight to each of the tree banks, and it would be even better because then we have more data. And turns out, yes, that's the case. That helps. And there is a lot of ways you can do that. Of course, people did a lot of work even monolingually, like if you have 3 different parsers, so each of them is good for something else, so it's a good idea to combine them together. So there was a lot of pre-existing work already, which I was able to build on. And so I'll just show the parse tree combination method, which turned out to be the most promising probably. So, well, tree bank concatenation is simple. Just take all the tree banks and concatenate them together. Well, it's good as baseline, but it has many problems. You cannot easily weight it, and just the larger tree banks get more power in the combination, and you cannot do much about it. You can just delete data, but it's a pity. So the parse tree combination method is relatively simple. It was invented by Segé and Levy in 2006 or something for monolingual parser combination. And so you train a separate parser for each of the tree banks. So if you have 30 tree banks, you train 30 parsers, either delexicalized. These experiments were delexicalized, so the numbers will be for delexicalized, but you can do it after translating into the target language and you have a lexicalized parser. And then you have this sentence, and you can just apply all of these 30 parsers to the sentence, and the parsers can then do voting. So let's see if I have 3 languages. So for this sentence, each of the parsers has a different graph as the output. So I just sum up these graphs, and I can see this edge was seen 3 times, this edge was seen twice, this edge was seen once. So I just sum up the parse trees. And now I can just do the maximum spanning tree, which I already showed in the Mst Algorithm, that when you have edges with scores, you can just, there is plenty algorithms to choose the best tree from that. So it's kind of easy to do. And what's even better is that you can easily add weighting. So what I did was to add the KL C+3 similarity, which I just showed. So for each of these parse trees, I know how similar the source language was to the target language. So I give more powerful vote to the more similar languages. So I still sum up the edges, but now it's weighted. And now I can maybe get a different parse tree. So probably a better one. So this is a method that worked very well. It has very nice properties because the weighting is easy when you know the language similarities. So you can very easily just multiply the ones with the weight. It's nice that you can naturally parallelize the training. So train the 30 parsers separately, and it's kind of efficient. In the tree bank concatenation, you just train a parser on huge data, and it took like 2 weeks to train. Yeah, you can or do not have to include the influence of tree bank size. So each of the parser has just the vote that you give to it. So it can be a 1 for each parser, or it can be a different weight. So it doesn't now happen that if the tree bank is larger, then the parser just gets more weight, which happened in the tree bank concatenation. A bit of problem is that now you have n parsers, and when you want to parse one sentence, so you really have to run the n parsers, take their outputs, and combine them together. So the parsing is a bit more complex, but it's still using the same parsing algorithm, just one more step after that. So it's not crazily complex. Yeah, I also did the parsing model interpolation, which didn't work so well. So I will just say the main idea. So the main idea is that maybe if the parser already outputs some scores for each of the edges, so maybe it means that if the score is higher, the parser is more sure about the edge. Well, that's true, but not fully. So what I try to do, of course, is just sum up these edge scores, similarly to the parsed recombination. And it's possible to weight it, of course. You can still multiply the edges by the similarity. But it turned out that it doesn't work really as simple as that, because the edge score that comes out of the parsing model is not the same as the parser confidence about how confident the parser is that this edge is the correct edge. It's a rough estimate. It correlates, but it's not the same thing. And there is actually at least one extensive paper about how to know how confident a parser is about the edge. And they introduced 3 different methods, like remove the edge and see how the total score of the tree drops, or just do 10 best possible parse trees and see in how many of them the edge appears, or just use the train model, which has some features and some weights, and just sample the weights around the weights a bit and see again in how many trees this appears. And this, at least according to their paper, is much more accurate than just using the edge score. But it's slower, of course, because there is some k, so the time is multiplied by this k, of course. It's harder to do, but it would probably get better results. So this is the comparison of the different methods for the multilingual setting. So in all of these cases, I used this KL similarity. I didn't use the other ones. That's future work. So the baseline was just the simple tree bank concatenation. Just put everything together, train it on everything. So that doesn't work so well. Then already when I just try to select the most similar language to use as the source language, this helps a lot. So it just transfers from one language to one language. Now the combination, so that's just sum up the trees with ones or with the weights coming from the KL similarity, and that works. That adds like 4 percentage points, so that's a good improvement. The model interpolation, it basically has the same score, which is kind of a disappointment because it used more information. So it didn't use only the existence of the edge, but it also used the score of the edge. So I hoped it would be better, but because of the problems I showed on the previous slide, it's not better. So that's nothing good. And in this case, actually, this was the Delexicalized Parsing over 18 languages this time. So here, the upper bound that I thought about is, let's try to use each of the possible source languages independently, and the one that has the highest score, so that's like the oracle source language. So if I had the target test data, so I can just use each of the languages and see which one gives the best score. So the average of that was still a bit higher, but not that much. It's just, 3 percentage points, so that's already quite close. Of course, still the problem is that still this is like 55% accuracy, which is very low, but that's just how it mostly is with these crossing methods. Okay, so that's everything. So I showed you how I deal with and how other people deal with parsing of low-resource natural languages. So the first possible approach is this delexicalized parsing, where you just remove the word forms but you have to assume that you have part of speech text in the target language, which is not very realistic. So it's turned out to be better to do lexicalization with machine translation. And I showed all of these problems it has and all of these solutions that didn't work for them. And then when you have multiple source languages available, then it helps really, really a lot if you are able to select the best source language or even to combine multiple source languages. That's even better. So there is still something, at least for me, to do. So I still want to look at the machine translation a bit, so really to try to, well, I don't do reordering, so if I have these noun adjective and adjective nouns languages, so it really breaks a lot. So I want to try to have a bit more, like to say, wiser MT that at least can do some reordering, maybe some, maybe like end-to-end, so if it translates two words to different two words, so maybe I don't know how these words belong together, but at least it could handle some other phenomena. All the experiments that I showed with the selecting or combining multiple sources, this was done on delexicalized parsing, so I want to repeat these experiments, but this time with lexicalized parsing. And in the end, when I know which of these setups are the best, so of course I want to combine them together to see what's the best parsing accuracy we can achieve by using these methods. And then obviously I want to put it into my dissertation and hand it in. So thanks.
Yeah, thank you very much. I think it was a kind of model paper. I liked it really very much. And wish you good luck with finishing the thesis. But
thank you.
Seem to be on the right way.
Hopefully.
So, questions, remarks, suggestions? Yeah.
So, thanks for a great talk. I would like to ask, how does your work compare with the modern multilingual multitask approaches with neural networks? For example, the paper Many Languages, One Parser, where they basically trained on all the languages, build up some embeddings, language universal, and also, for example, use the vowels features. So,
that's a dimension I didn't really touch on. This work is a bit different because it's not really for the cross-lingual case. It's like rather the multilingual case when you do have some data annotated for the target language and you just add data for other languages to it, which seems to help in many cases. Like we already saw that with Slovak, that probably when we add Czech data and Slovak data, so we would get even better results than just with using one of the three banks. So that's basically very similar to what I do. It's a different setting, so I didn't do any experiments in that regard, and I don't really plan to do that, but I do acknowledge it's very related.
Thanks.
You mentioned that you were trying to use some morphological segmentation. Which tool did you use, or which approach did you use to do that?
In the basic experiment, I tried to use Morphessor, and I tried to play with some of the parameters to push it to do the segmentation similarly in both of the two languages. I then tried some Bayesian sampling for the segmentation, which I implemented myself, and either I did it incorrectly or it just doesn't work that way. Then there is the paper of Snyder and Berzilay, who have this joint morphological segmentation and alignment in parallel setting. I was unable to find or to get the tool that would do that, and I tried to re-implement that tool. It didn't really work well. I think I did some mistake again. So yeah, and what I didn't do, but I planned to do at least, was to use a supervised morphological segmenter. Because for a few languages, like at least for English, there is like data labeled with the morphological segmentation. So the idea was to do supervised segmentation in English and then just try to project the segmentation into the other language. And I didn't get to do that in the end. I might probably want to try, but somehow I lost most of trust in the morphological segmentation now, because all of this just worked very badly. Yeah. Wonder if Derinat would be helpful in that case, but I don't know.
I'm working on a segmentation tool for Czech using data from Derinat, so maybe keep in touch with me.
Yeah, so yeah, I could still try that. Why not?
I have a question that have you tried measuring how much okay, if you train or like with this projection or from different languages, if you train a parser from 30 languages, like and then you compare it with the typological, actually the linguistic typology, does it correlate, or have you tried it?
So, like whether
so if you measure
it, information correlates with this empirical information, or
for instance, if you get only the attachment scores, and from one language it's better than from, for example, from Czech to Slovak, it's better than from English to Slovak, and if you compared it with, it would be interesting to compare if it really correlates.
But that's what I said partially, that it's not that easy, because this typology, it's not like one-dimensional thing.
Yeah, it's multi-dimensional.
So it's hard to compare it like meaningfully. So actually, I will have a paper on TLT in January here, where I do error analysis of cross-lingual parsing, and where I try to project from English to I don't know, 30 languages again or something. And when I ordered them by the score, so yes, the best results I got for Germanic and Romance languages. Actually, the best results I got for Portuguese, even better than for German or other languages. German doesn't work very well with English, actually, because it has a different word order. So yeah, so you can, so from the results, yes, you can see these differences that are based on the typological differences, and in case you know the typology of both of the languages, so you can often guess or look into the data and understand why the scores look like that, why are they good, why are they bad. Yeah, I haven't found any way to do that like automatically in a complex way to see, okay, it works like that.
Yeah, it's so, maybe like
but yeah, it's possible, like when you look at like two languages or a few languages, so you can look at it and see what happens there and what things are important, what things are less important. So obviously, if one of the language has determiners and the other one doesn't, so that's like really important. The word ordering is very important. Yeah.
I mean, then this could be a like thing to look at the theoretical linguistics or the typology of languages. You can make these experiments like from many languages, and then you can. So you mentioned Portuguese. That some language can show up in a very high position, even though you haven't thought about it. That it's very similar to the language, just because it's from the different family, or you. Yeah. So.
Yeah. So I've done a bit in this direction, and yeah. So basically, people have already done that if we can say that vals is a proxy for language typology, which it basically is, so the linguists just label the languages like, does it have SOV or SVO or OVS or whatever, and does it have adjective noun or noun adjective or whatever, does it have prepositions or postpositions or what? So yes, people have already found that at least some of these features from the atlas are very useful to predict which languages will work better with other languages in the parsing. And some of them are less important. That's also true. But it's, yeah, so I've seen several works touching on that. I've touched on that, but I cannot really imagine like what would be the ultimate way of doing that, like to analyze it really properly in all directions. That's probably,
yeah, it's more like a cherry picking.
Yeah.
Okay, thank you.
Yeah, I have just one very marginal point relating to the terminology. I must say that for the in the first, or I don't know how many slides at the very beginning, when you outlined your problem and the possible solutions, your use of target and source language or target and source tree bank was a little bit misleading for me, because I can think about source and target in terms of machine translation, source language translated into target. And it seemed to be at the very beginning, I even wanted to point out that you use the words in a different way. But then I understood how you use them. So, and I don't know have any replacement proposals, but maybe when you present the problem, you may just say something about that. Because
yeah, it's true. Like, fortunately, in the end, when I do the machine translation, so the terms match. So really, the source is the source, and the target is the target.
Yes.
Which could be done differently, and then it would be even more confusing. But
no, it was just the very beginning of your talk.
Yeah.
Okay. So, if there are no further questions, so I wanted to thank the speaker again for his very nice talk today.
Thank you.
I should say that this is the last occasion we meet at our seminar for this calendar year, but I do hope to meet you during the next calendar year, and if we don't meet before then, I wish you a good start to the new calendar year. So thank you again very much.